Welcome everyone. Today we're going to be continuing on with our oscillating systems and we're going to be introducing a new concept which is damping. Now hopefully you've seen some of this before. If you haven't, that's okay. We're going to go through it. I'm going to give you the basic concepts in this video, and then what we're going to do is we're going to get the general solution to this system over here with the spring K and the damper C. The dampers are so similar to springs. You really don't have to understand it fully to really be able to do these questions. So I'm going to give you a brief explanation now. The spring force, as you know, is just F spring is equal to negative K times X. Well, for a damping, the damping force, FD is equal to negative C X dot. So it's exactly the same. It's in the same direction as a spring. It'll be going in the opposite direction to the motion of the block. That's the force vector, times this C constant, which is just the damping constant. And then this is our velocity. So instead of displacement, the force of a damper is a function of velocity. So that's really the only difference. If we had a displacement here, then it would be exactly the same as a spring. So let's just jump straight into the derivation of the equation of motion for this system. We're going to have very similar terms to our spring mass example because we've essentially got the same component. We're just adding this damping term. So firstly, we're going to start off with a free body diagram. Now I encourage you to pause this video and just give a quick sketch of the free body diagram to try to work out what direction these forces are going. Do note that I changed our positive direction from some of my previous videos. So, just try to work this out because this is the first step in any oscillating or spring mass system problem to work out the direction of our forces. So just pause the video, give it a go. So this is what I got for my free body diagram. You'll see as we move the mass up in the positive direction, the spring and the damper will be trying to pull the mass back down. That's why the forces are pointing down this time. So first things first, once we've done our free body diagram, we want to try to get our equation of motion. And by that we do sum to forces in the x direction. And this is just going to give us, so you'll see that these kx and cx dot, they're just on the left-hand side, and I'll bring them over, and this is what I'll get. So this is our equation of motion for the system. Equation of motion. That's good. So now we're in a similar spot where we were last time. We have to solve this equation to try to find a solution such that it satisfies it. So the first thing we want to do is we want to try to simplify this equation a bit further. So what we'll do is we'll divide through by the mass, and that gives us this other version. Now, to make our life simpler, I'm going to introduce a few new constants. One of them you've seen, which is omega n is equal to k on m square root. And then the other one is the damping ratio, which is equal to c on 2 root km. Now we're going to go into more detail as to what the damping ratio is later, but all you need to know now is that it equals this. So what we want to do is we want to substitute this in such that this equation is still true. So it just so happens that 2 times the damping ratio times omega n is equal to c on m. Now if you don't believe me, just chuck these quantities into the equation and see if you get c on m. So what we do is we just chuck them in here, and this gives us an equation with similar terms, and it may look a little bit more complicated, but it's going to be good for us in the long run. So we'll just come down here, and you'll remember from our last video where I went into probably a little bit more detail that we assume our displacement has the form e to the lambda t. We assume it has this form. So I'm not going to go through all the details, but if you take the first and second derivative of this and substitute it back into this equation, what you're going to get, now as this term can never equal 0 because it's an exponential, This is our characteristic equation in here and must equal to 0. So to get the solution for this equation, what we're going to have to do is we're going to have to use the quadratic equation. I'm sure everyone's familiar with the quadratic equation, but if you're not, the quadratic equation is equal to where b, a, and c are coefficients in the polynomial. So what we want to find is lambda is our unknown. So what we have is, this is the b term in here. This is the b term. So we have minus 2 damping ratio omega n plus or minus the square root of minus 4 times 1 times omega n squared. That's just because this is c's omega n squared. All right, and then this is all going to be divided by 2 times 1. We're just going to simplify this down. So if you bring the square in here, you're going to get 4, and then you've got a common factor of 4 under the square root, so you can bring the 2 out. Similarly, you've got omega n squared and then omega n squared, so you can bring out an omega n term. And then all you're left under the square root sign is the ratio squared minus 1 divided by 2, which means that we can cancel out these 2's. And this just gives our final solution as lambda is equal to the damping ratio times omega n plus or minus omega n times the square root of the damping ratio minus 1. So this is our final solution of our characteristic equation. And you can see that depending on what our damping ratio value is, we're going to get different types of solutions. If this ratio is less than 1, what we're going to get is we're going to get a complex number here. If it's greater than 1, we're going to get a real solution. And what happens if it is 1? Well, we're going to talk about all of this in the next video, and I'm going to break it down step by step as to what it means and what sort of damping we get when we choose our damping ratio. So if you like this video, please like and subscribe so I can bring you guys more videos in the future, and join me in the next video for an in-depth review of damping.